A standard normal distribution has a mean of 0 and standard deviation of 1. A score in this distribution is not represented by x, it's represented by z. Since the standard deviation is 1, a z-score of 1.5 implies the score of interest is 1.5 standard deviations above the mean. A z-score of negative 2 implies a score of 2 standard deviations below the mean. A practical example might be measuring the temperature in Celsius on a cheap thermometer at standard pressure at the moment water freezes. The mean temperature is 0 degrees Celsius, but random chance fluctuation involves a standard deviation of 1 degree. But the standard normal distribution of z-scores is more important than temperatures. It is foundational to research and analysis. Most textbooks contain a standard normal table. Here's one I created. It is a cumulative relative frequency distribution. Remember the ogive, how it adds up frequency until you get to a variable value that has 100% of scores below it? This is what this table is doing. If we go to a z-score of 1 and look at the column, we see 0.8413. This implies that 84.1% of the z-scores are located below z equals 1. Recall the empirical rule of 68, 95, 99.7%. This 0.8413 is where the 68% comes from, because 50% of the distribution is below the mean of 0, the z-score of 0, leaving 34.13% from the mean to z equals 1 standard deviation above the mean. With symmetry, there's also 0.3413 between z equals negative 1 and z equals 0. Thus, there is 0.6826 from 1 standard deviation below the mean to 1 standard deviation above it, 68%. Here's the best definition of a z-score. It's the position of a score on the x-axis in terms of the number of standard deviations from the mean. Recall that a standard deviation is roughly the average distance of all scores from their mean average. Therefore, a z-score of 2.4 is 2.4 standard deviations above the mean. It is more than twice the average distance of a score from the mean. Thus, it's more extreme. In fact, we can see from the table that it would have 99% of the scores below it. The table allows us to find proportions below a z-score to the hundredths place. If we wanted this for z equals 2.48, we would start at 2.4, but then move right until we were under the column of 0.08. 0.9934 is the proportion of scores in any normal distribution below a z-score of 2.48. Since 100% of scores are contained under the curve of the normal distribution, then the proportion of scores above z equals 2.48 is 1 minus 0.9938, or 0.006. Get used to this notation. For now, I just read it as the proportion of scores above z equals 2.48, but soon we're going to recognize it to be probability. We will read it as, if a score is randomly selected, the probability it would exceed a z-score of 2.48. Find the probability that z is at least negative 0.72. The negative z-score implies a score 0.72 standard deviations to the left of the mean. Here is another page that contains negative z-scores. The table displays the cumulative relative frequency below negative 0.72 standard deviations. This value is 0.2358. We want the complement of this, the proportion above, so we just subtract the 0.358 from 1 from 100%, and this is the proportion of scores above z equals negative 0.72. I am showing you the proportions visually on a normal distribution. It's wise for you to sketch a normal curve for such problems and organize the information by showing proportions under the curve in relation to the key z-scores. Use the standard normal table to determine the proportion of a normal distribution between z equals negative 0.35 and z equals 2.04. Here are the endpoints of the interval. Take the entire proportion below the z-score of 2.04 and the portion of the scores below z equals negative 0.35, subtract these proportions. The difference is the proportion of scores in any normal distribution between 0.35 standard deviations below the mean and 2.04 standard deviations above the mean.